first of all, a definition of a polynomial function is any powers of x, okay, where we would say a couple of important definitions here. We call the number in front of the highest power as the leading coefficient. And all of the exponents are positive whole numbers. And this makes a polynomial function. Now, what I would like you to do right beside this is write the following notes. First one we're going to look at is odd functions. An odd function is when the highest exponent is odd. So an x cubed graph is an odd function. An x to the 5 one would be an odd function. And we're going to make a little note and we're going to see what this means in the next little bit. We're going to say that its end behavior, where the graph ends, is going to act like a line, because you've graphed lines before. You know that lines with a positive slope go up from left to right. Lines with a negative slope go down from left to right. And even functions again, hopefully this is obvious, the highest exponent is an even number. Their end behavior acts like a parabola. So what does this mean? Well, we're going to look at, we'll start with lines and parabolas just to remind ourselves what do lines look like and what do parabolas look like. Here we have a line. If you have a positive leading coefficient with a line, in other words, here in front of the x there's a positive 1, that would mean its slope is positive, and you know that positive slopes always go up from left to right. Negative slopes always go down from left to right. So I'd like you to take out your pen and add arrows onto the end here, because where those arrows are the end behavior, or what we call the end behavior of the graph. Where does the graph end? Where would you put the arrowhead on? If it's a positive line, it goes up forever from left to right. That's where you would put your arrowheads. If you had a parabola, any parabola where the leading coefficient is positive, well, those parabolas open up. So your end behavior, both sides are going up. And if you have a negative coefficient, that flips your parabola. And we learned that if there's a negative a value in a parabola, it opens down. So if the leading coefficient is positive on a parabola, it's opening up with your end behavior pointing up on both sides. If it's negative, it's pointing down. And we can use this information for x cubed, x to the 4, x to the 5 graphs. So what does that mean? Well, when we go to an x cubed graph, if I saw this equation, I would say x cubed is odd, its end behavior acts like a line. If it's positive, I say a line goes like that when it's positive. So its end behavior has to be up here and down here. Do you see that that works out for the x cubed graph? But it might have some extra stuff in the middle. We're not worried about that right now. Right now, we're just thinking about where does a graph start and where does it end. A negative x cubed graph, well, if it acts like a line, its end behavior says it starts up here and goes down there. You see that this matches up. just that there's some extra stuff in the middle. Now we get to an x to the 4 graph. An x to the 4 graph is even, so I would say it acts like a parabola. A parabola that's positive, there's its end behavior, and sure enough, this x to the 4 graph has that same ending. Just has extra stuff in the middle. And same thing with a negative x to the 4 graph. We think of a negative parabola, its end behavior is down there. Sure enough, the end behavior of this graph matches up. And we could keep going forever with these. There's one more, they have the x to the 5. You're like, that's odd, it's going to act like a line. So my end behavior should be up here and down here. Sure enough, that's where those arrows are. And with a negative x to the 5 graph, end behavior should be here and here, and sure enough, that's where those arrows are. This is going to be one step to help us graph things. What we're going to want to be able to do by the end of this unit is to come up with a technique to get a good graph of what's going on. And the first thing that we have right now is where the graph ends. We just don't know what's happening in the middle. So when we go to, oh yeah, and if we look at what the textbook describes, I think what we just said in our note is so much easier, okay? This is what they've got, and I've told you if it's an odd one and it's positive, you have to think of a line. How easy is this to remember? Super easy. If you had to memorize, as x goes to negative infinity, the graph falls to the left, and as x goes to positive infinity, the graph rises to the right. That's just what this little picture just did, which is way easier to remember than all of that explanation. If an odd function is negative, it acts like a line. There's your end behavior. Much easier than their definition. I'm never going to ask you to write these things out in words. I'm just going to ask you to apply it. And same thing with the even ones, right? How much easier is it to remember the parabola and say, oh, that's my end behavior, rather than this. Same thing, if an even is negative, I think of a negative parabola. There's my end behavior. That's a lot easier than that. So when we talk about end behavior of graphs, they're either odd or even. Odd ones act like lines, even ones act like parabolas, and all we have to look at is the leading coefficient, the number in front. Is it positive or is it negative? Some other definitions that actually become way more important when you get to calculus. Graphs have local maximums and local minimums. Here we have a negative x to the 4 graph. We would call those 2 points local maximums. And when they're talking about a local maximum, it's like you're imagining a small town. Here's a small town, put a circle around it. Everything that's in that small town is in that circle. And can you see that that point is the biggest one in that small town, right? We have somebody in this class who is the tallest. They are a local maximum in this class. They are not the tallest person in the world, unfortunately. Right? You would have to really be in a bubble to go, I think I'm the tallest person in the world because all I do is spend my entire life in this math class, and these are the only people I've ever seen, and I'm the tallest. So I must be the tallest in the world. No. So we have local maximum, just like there's somebody, if we draw a little town around this one, there is somebody in this class who is the shortest. And they are the local minimum for height in this class. Okay, let's go to example 1. And they ask us to sketch these graphs. Now, we are going to learn some very good techniques, but for right now, what we're going to do is go back to our most basic graphing technique that we've learned right from grade 9, which is if you want to graph something, you could just find a bunch of points and plot them. Okay? What we already know is that in A, it is odd with a positive leading coefficient. So its end behavior is going to look like this. We know where the graph has to go on the two ends. Then if we want, if we want to graph this, what we could do is just find a bunch of points. Like what happens when x is 0? Oh, y is 0. So I have a point. What happens when x is 1? You would have 1 minus 3, you would get negative 2. And you'd get another point. What happens when x is 2? You'd have 8 minus 12, you would have negative 4. What happens when x is 3? You would have 27 minus 27, you would have 0. And we could keep going. And the more points that you have, the more accurate you would get. One of the things that's annoying about a table of values is you might feel you have to do a lot before you're done. Okay? So maybe I'm like, well, first of all, it kind of looks like I have this right now, right? That part is good. Because I can sort of connect dots in between, but I don't know where the rest of this graph is going. So I might plug in another number like negative 1, and negative 1 would be negative 4. And anytime you draw a graph, you do have to do some label. So now I have this amount. And if I think about an x cubed having only 3 places, and its end behavior, I might be able to say this is what I think it looks like. This isn't perfect, but it seems to be a good picture of what's going on. Okay? So this is our table of values. We can plug in as many points as we want, plus you have, from the end behavior stuff, what we have already, an idea of what it looks like. So the only thing that I'm going to do for part B here, in part B, I'm going to get you to say, hey, it's a negative even function. That's where the end behavior is. And you can circle questions 5, 6, and 8 on this one.